Hello. In the last lecture, I have introduced the endogeneity problem. The endogeneity problem is when the exogeneity assumption fails in the classical linear regression model or in any kind of regression model. So without the exogeneity assumption, you cannot identify the parameters of the regression model. So it's one of the most common and one of the most critical identification failure problem. Today, in the last lecture, I gave you some background concepts and examples where the endogeneity problem arises. And today, we are going to approach to the problem a little more rigorously, mathematically. Still very simple in a simple model. And then I will introduce you how to fix that. Fix is a little bit, actually very simple. Let's see. Okay, let's think about the simplest possible linear regression model. X, the explanatory variable x is one-dimensional, scalar, and there is no intercept, so simple. But the problem here is, the major difference here is that the correlation between x and epsilon is unknown. We don't care, we don't know. So compared with, if you think about the classical linear regression model, we know this because of an assumption, because of the exogeneity assumption. We knew that the correlation was zero. The correlation was zero in the classical linear regression model, but now it's free. It's not restricted. It could be any number, could be zero, could be non-zero. So that's the main difference. Without this assumption, then we fail to identify beta. We cannot identify beta. To prove that, I will show that there is an observationally equivalent parameter to the true parameter. So this is a simple argument. Choose any non-zero number, or non-zero number A different from zero. Any number, does not matter. Just then if you define beta tilde this way, beta tilde is beta 0 plus A, so it's different from beta 0. There must be a comma here, sorry about that. So beta 0 and beta tilde are different. And to compensate this increase, I will subtract AX from epsilon and define epsilon tilde. So I define the new and different parameter value and a new error term. And then you have y tilde defined as beta tilde x plus epsilon tilde. And replace beta tilde and epsilon tilde as they are defined, the expressions here. Then it's easy, very easy to show that in the end y tilde equals to y. So it's really easy, simple. Then y, and this model, or y tilde model, is still a linear regression model. It satisfies the other assumptions like linearity, full rank assumption, and the second moment assumption. So the only problem with y tilde is the lack of the exogeneity assumption, but we are not restricting exogeneity anymore. So without exogeneity, you cannot tell beta tilde from beta 0. So as you can see, A can be any number. A is any non-zero number. So there are an infinite number of observationally equivalent parameter, right? So beta tilde can be any number. So it's not just between two parameter values. So beta can be any number, and you cannot tell what is right, what is wrong. So there is no hope at all. Nothing can be done. The comparison, here is a comparison with the full rank condition. So far we learned two types of identification failures in the linear regression model. One was multicollinearity, and the other was the endogeneity problem. And let me compare how they differ. First, the multicollinearity problem is like easier to handle, because easier to detect, because multicollinearity is about x1 and x2. Both are observed. So you just need to check if they are correlated, how much they are correlated, or how much multiple variables are correlated to each other. So at least you observe the variables, so you can tell whether they are correlated or not. Multicollinearity problem can be detected if you are careful enough. However, the problem with the endogeneity problem is it's about this assumption. The assumption is about x and epsilon. It's now correlation between x and unobserved epsilon. So you cannot calculate this correlation at all. So the idea is to calculate, to detect, you want to check if the correlation is 0 or not. But if you want to calculate the correlation, you need to know epsilon. You need to know epsilon, but the only way to observe epsilon is to identify beta 0. So epsilon is not directly identified, not observed. So to calculate epsilon, you have to calculate it as y minus beta x. But beta is not observed, not identified, because we don't know the correlation. So it's going around. So there is no way to detect, to calculate the correlation between x and epsilon without assuming this. Once you assume this, then you don't need to test it. So already you made the assumption. So there is no direct way to detect the endogeneity problem. The main idea is this assumption is about something unknown. So you cannot detect it from the data. And the second difference is that the full rank condition, if the multicollinearity problem arises, then there is some computational problem, which is actually good. It may be annoying, so when you see the error message, but it's nice because at least it tells you that there is a problem. So if the multicollinearity is severe, then the inverse cannot be calculated, the inverse matrix cannot be calculated on a program, like I explained it as a kind of out-of-memory problem. And then you can expect, this could be a multicollinearity problem. However, the endogeneity problem does not cause any computational problem. Even if there is an endogeneity problem in your data, still your program will give you something, and does not say anything. It never show any error message. So you cannot detect. So that's exactly the same problem as number one. You cannot detect from the data whether there is an endogeneity problem or not. So it is purely your mind game, in your imagination. You have to check if the variable is endogenous or exogenous by yourself. And the third difference is that, so think about, so suppose that there are 3 variables and 2 of the variables are multicollinear, and then in most cases the third variable, which is irrelevant to the multicollinearity problem, is not affected. So there are some unaffected variables that if they are irrelevant to the problem. However, in the endogeneity problem, almost always, all the variables are affected. So for example, x1, you have x1 and x2. You know that x1 is exogenous but uncertain about x2. So x2 could be a problem potentially. Still, it does not imply it is still, even though x1 is totally fine, still the problem in x2 affects x1's coefficient. So x1's coefficient could be contaminated, even though x1 itself is fine, but because of X2's problem. So it's more serious, more causing more problems. So overall, that's why I made up a separate chapter for the endogeneity problem. Let me explain with some graph. So the typical example of the endogeneity is, so we would like to regress earnings, your wage, on education and ability. Suppose that your earnings is determined by education and ability, and I will assume that additional education, 1 year, 1 unit of education increases earnings by beta, and 1 unit of ability increases the earnings by gamma. And in the ideal, in the true relationship, however, the problem is that ability is not observed. You never observe the true ability. It's say diligence or your passion for like your hardworkingness, or like many different abilities are not observed. Then the problem here is, so then okay, you cannot observe ability, but still, if you could estimate beta, then that would be fine. You are interested only in beta, not in gamma. Then would it be fine? No. So you want to estimate beta, and the problem is in ability. Ability is not observed, but still education is, the beta is not correctly identified. And the reason is because education has direct effect. This direct effect is what you want to estimate, right? Holding the ability fixed, and I'd like to see the marginal effect of education on earnings without changing ability. However, the problem is higher education usually implies higher ability. So PhD is like, it's typical common tendency. When I see a person who says she has a PhD degree, then I can assume that it's more likely that she is more intelligent than, like, academically intelligent than an average person. So higher education implies higher ability, and then higher ability implies higher earnings. So this is indirect channel. You cannot control for this indirect channel. Indirect effect is always, it exists, and it cannot be distinguished from the direct effect. What you have is just how these two are linked together. This is what you observe from the data. So there is education. Excuse me. You only observe higher education implies higher earnings. It could be caused by two different channels, but there is no way to distinguish these two without observing ability. So this is endogeneity problem. Ability is the error term. So education implies higher education implies higher ability, which means correlation between them. Correlation between education and error term, and as a result, you don't know what's going on. Now, how to fix it? Its fix is pretty simple. Okay. One more thing. So this indirect effect is basically from some kind of omitted variable bias. So this variable is omitted from the model or from the data. So you have to imagine, so higher education, 1 unit increase in education implies delta increase in ability, and delta increase in ability affects gamma times delta earnings, right? It's straightforward. Delta times gamma is the indirect ability you can expect from this simple model, and then total effect will be beta plus gamma times delta. Beta plus gamma times delta is the observed correlation between education and earnings, observed relationship. It looks like 1 unit increase in education increases earnings by beta plus gamma delta, right? These two, gamma delta and beta, are combined, cannot be distinguished. So then how can we fix it? We are going to introduce another observed variable. So this problem cannot be handled within this 3 variable setup. So we have to bring in another new variable. We are going to call that IV, instrumental variable. So anyhow, suppose that there is another variable, and what we are going to assume here is instrument, this new variable does not have direct channel. Direct channel does not exist, right? That is number one assumption. Number two, the new variable does not imply, has no correlation with ability, the error term. So ability has nothing to do with the new variable. So this indirect channel, the effect from IV on earnings, is not delivered through this channel. So this channel is also blocked. And then finally, it is correlated with education. This channel must survive. There must be remaining channel, and so this channel should be the only channel that the effect of IV on earnings is delivered. So the effect is transferred only through this way. Then all the other bridges are broken, and we have pi, beta, gamma, and delta. Delta is hidden here. So that's only correlations we have among these 4 variables, right? And then what we have here is we can calculate the relationship between the new variable and the earnings. The new variable and the earnings are observed, so you can calculate their relationship. So you can calculate how much earnings increases when the new variable increases by 1 unit. You can calculate that from the data, and then later, by our assumption, you can say that those effect is actually this. So pi. So this effect can be decomposed into IV of a new variable affecting education, and the increase in education affect the earnings. So this is the only channel. So the effect of IV on earnings can be explained only by this channel. There is no other way. And then what you need here is you can calculate this, and you can calculate this, because you observe IV, the new variable, and education. So you can calculate how much education increases when the new variable increases. So then if you know this, then beta can be calculated. That's how we identify beta in an endogenous when the endogeneity problem arises. Okay, I hope it delivers the idea. That's too long. See you later.